Good afternoon, ladies and gentlemen. John Belkowitz here. We're going to get into some more of this statics engineering. Working on a simply supported beam, which we did last time. I believe we did a uniform distributed load and then a point load. We're going to be taking it to the next level, and we're going to be doing a combination of a distributed load and a point load. So I'm going to go ahead and start creating all that stuff right now, all the background. So stay tuned. It's going to be awesome. So I got my simply supported beam. I have 10 pounds per linear foot for 10 feet, and then in the middle of the span, I've got a 100-pound point load, and then I have 5 pounds per linear feet for the next 10 pounds. So the first thing that we want to do, and gosh, did I wish I have a black magic marker here, is I want to start doing the math. And to do that, I have to do my free body diagram. And assuming, oh, there it is. I didn't lose my protractor. So first thing I want to start out with is my FBD. And my FBD is going to be a mathematical representation, or something, a representation that I can use to start doing the logic or the math to start figuring out my reactions. So with my FBD, and before I draw it, I also want to draw my sign convention. So we're saying X direction, Y direction, counterclockwise. All of those are positive. All right, and now we're going to do our simply supported beam, and to a certain degree, it's redrawing everything that we just did, but now with the, proper arrows for the reactions. And I'm going to call this A over here, and this B. So this is AX, and this is AY, and this is BY. Now you should be seeing the same thing that we did before. This is not any different than the procedure that we took. It's just now there's a certain accountability for our math. All right, so now I start doing some of my math. And I'm going to focus some of that math over here so I don't confuse it. So my reactionary force for my 10 pounds per foot is going to equal 10 pounds per linear foot times 10 feet equals 100 pounds. And that's going to be at 5 feet. Then I'm also going to have I have my point load, but now I have another distributed load. So my reactionary force for my 5 pound per linear foot load is going to be 5 pounds per linear foot times 10 feet equals 50 pounds. And that's going to be at 10, 2.5, 12.5 feet. Okay, so, and then of course here, and that's going to be an extra, oh, sorry, not 12.5, whoop, 15 feet. Look at that math. That would have been fun. Gone through all that work. So that's an extra 5 feet there to give me that 15 feet. Okay, so I'm going to go ahead and draw those all in. Now please bear in mind, we're still going to take into account that these are distributed loads, but again, when we're trying to figure out the moments and what have you, we have to write that representation of what that reactionary load and where it's going to happen. And when it comes to distributed loads, we go, this rectangular distributed load, we go with the center of that, rectangle. If it was the full size, we can go to the center of that, but these are change in distributions. If it's a triangular load, we're going to go 1/3 from the peak, or the tallest peak of that distributed load, for where that reaction is going to be, 1/3 from that peak. Okay, so we got everything written in. Let's go ahead and start doing some math here. Oops. So we're going to start it off by doing our sum of forces in the X direction. And the reason why we do that is because it's the easiest thing to do. Sum of forces in the X direction, we have AX. We go down the line, and there's nothing else in the X direction, so AX equals 0. We're done. We can check off AX equals 0, put a nice little fancy box around it. Next thing we do is sum of forces in the y direction equals 0. Now this is where we came up with an equation that had multiple unknowns, 2 unknowns in our last video. So we're going to run into the same thing here, and it's probably going to be our our AY chutes and ladders. Okay, that's a horrible marker. It's going to be our AY and our BY, and the way we get past that is by using our sum of moments. So we're going to do that again here. But let's go ahead and focus on this. So we got our AY in the positive direction, minus 100 pounds, minus 100 pounds, minus 50 pounds, and then we have a plus BY, and that all equals 0. So if we go ahead, we'll write equation number 1. We'll say AY equals 250 pounds minus BY. So that's equation number 1. All right, and then we'll leave here is equation number 1. AY equals 250 pounds minus question mark, and we'll fill that in later, equals. Okay, so now we've got our first equation, but we have 2 unknowns, our AY and our BY. We have no clue what they are, so we can't solve using just one equation. If we want to solve for 2 unknowns, we need at least 2 equations. So our second equation is going to come from summing our moments about point A equals 0. All right, so this is where we're going to sum our moments. And the reason why we sum our moments there, so we can cancel out our AY, our AX and our AY. Remember, when we're in the line of action, we can't multiply by a perpendicular distance. Therefore, we end off with an equal or a 0 for those reactions when it comes to our moments. So I'm going to go ahead and start from my AY. I go this direction with my first 100 pounds, so that's going opposite to my sign convention. It's going clockwise, so minus 100 pounds times 5 feet, and there's my distance. And I go down my next, and I got another minus 100 pounds because it's going clockwise, but now it's at 10 feet. And then I go to my next one, minus 50 pounds, and that's going to be times 15 feet. And then finally, I've got my plus BY, and that's because that's going with my sign convention. And again, here's my sign convention, and that's at 20 feet. And that all equals 0. Okay, so ultimately what I come out with here is, what does my BY equal? So my BY, if I bring everything over, so this is going to be plus 500 foot-pounds plus 1,000 foot-pounds. And again, the reason why I'm at foot-pounds, I'm multiplying my 100 pounds times my distance, and that's what our moment is, force times distance. And then finally, I think that's 750. Oh, I need a calc. Yeah, folks, don't ever try to be tougher than a calculator. Ain't nothing wrong with using a calculator here, because it really just messes you up. And then, of course, all that stuff filters down. So never be tougher than a calculator. We're going to divide all of that by 20 feet. That came from our BY. So let's go ahead and do that again. So we have 112.5 pounds, and it is in the positive direction, which affirms what we originally wrote. So we don't have to change up our FBD. But now we've got to get back to our AY. So our AY is going to equal to 250 pounds minus 112.5 pounds. And what does that equal?
137.5.
Sorry. Let me do it this way. So AY equals 137.5 pounds. And this is also, we didn't do that. We did a box. So here we got AY equals 137.5 pounds. And over here, BY equals 112.5 pounds. Now, when we did our point load and our distributed load that was equal across the entire span, both of these were equal. Now when we do it, when we have an unequal distributed load, it seems like our AY is sitting heavier and our BY is sitting a little bit lighter. And that should make sense because remember, our reaction is trying to resist the load, and in our picture and in our free body diagram, we've got a higher load as we get closer to the AY compared to the BY, where instead of it being 100 pounds, now we're going down to 50 pounds. So now we're going to go ahead and dive into the math a little bit more. But I want to start by looking at the shear diagram. First thing that I start out with is I got my free body diagram, and now I know that my beam is all done, all the math is done. I could just read my math, and then we have a story to be told over our shear diagram. So if we assume that this is 137.5 and we already have pounds in our y-axis, this is where our reaction starts. So this is the first thing that we see. Now we go across 10 feet and there is a negative, constant negative 10 pounds for every linear foot. So if I do 10 times 100, that ends up getting me to, so 100 minus 37.5, that ends up getting me to 37.5. And that's going to be constantly decreasing by 10 pounds per linear foot. But remember, I also have a point load of 100 pounds. So we're pushing that down, and we have our negative 62.5 pounds. Now remember, we still have a reduction over every linear foot, but now instead of it being 10 pounds per linear foot, it's 5 pounds per linear foot. So we're going to go down another 10 feet. Now it's 5 pounds per linear, or it's 5 pounds per linear foot. So that takes us down 50 pounds. So that should take us, Leslie, you want to confirm this? Negative 62.5 minus 50 pounds should give me 112.5?
Yep.
And then, of course, we know our reaction at B was a positive, oh, I got it right, sorry, minus 112.5 pounds. And we know that B was a positive 112.5 pounds, and that brings us back to 0. And of course, that's the most important thing. We always have to bring us back to 0 because that means we have a stable system that we've created. One, it's statically determined, and two, it's a stable system because all of our forces equal, so it's a static and stable system. Good stuff. All right, so we've got a story here, just like we had with the shear diagram, but now we can't look at the beam. We have to look at the shear diagram for our story. So we have to take the area under the curve to determine where we're at on our shear diagram. We have 1, 2, 3, 4 areas to go for. So the first one is, you ready for this?
Yep.
0.5 times 10 feet times 100. Now the reason why I did that is this triangle goes from 137.5 pounds down to 37.5. So the height of that triangle is 100 pounds. The length of that triangle is 10 pounds, and because it's a triangle, 1/2 base times height gives us our area. So what do we have here? So area 1 equals 500. Area 2 is equal to 37.5, that's our height. Our distance is 10 feet, those 37, this is pounds over here. 37.5 pounds times 10 feet, it's a rectangle. So what is that, 375 pounds? Area 3 is gonna equal to 62.5 pounds times 10 feet. Equals to 625 pounds. And then area number 4, I'm running out of room. Area number 4 is going to be 112.5 minus 62.5 is 50. So area 4, the height of that triangle, it's 0.5 times 50 pounds times still 10 feet. And that equals, so 0.5 times 50 times 10, is that 250? Mm-hmm. 250 foot-pounds. So, almost done. So, area 1, area 2 gives us a total area of 500 plus 375. So, that should be what, 875? So, we have 875 for our foot-pounds. And then on the other side of that, we got 625 plus 250, which is 850, right? 620. No, that should be, that's 875. What am I talking about? Yeah. Sorry, sometimes that, I tell you, that's what I'm saying. A calculator is always going to be your friend. Okay, so because we have that constantly decreasing curve, a triangular curve, we're going to end up having a parabolic curve. We're just taking the integral of that previous chart. So we have a very high value here. That means we have a very high gradient here. And then we have what looks like a 0 gradient here, so it plateaus. And then, of course, here we're back to a very high gradient. So we end up looking, and this is a very ugly parabola, but we end up looking something like that. Okay, so thanks for joining us today. Hopefully this helped you out, working with that basic engineering statics and principles. If you have any questions, any concrete concerns, don't forget to like and subscribe. Let us know how we can help. Have a great day. Stay safe out there. Go concrete!
Beat asphalt.